This is the first ever image captured of a black hole. It was taken by the Event Horizon Telescope, which incorporated radio observatories across the globe to give us the resolution needed to image this cosmic behemoth. But recently, theorists have begun to wonder if it really is a black hole after all. And if it isn't, what else could it be?
I think what the public should pay attention to is that for the past about 20 years, astronomically, it is becoming more and more established that there are black holes at the center of every galaxy. I put some quotation mark here because it turns out we have not really proven that they are absolutely 100% or with a high confidence level they are black holes.
We are reasonably confident in Einstein's theory of general relativity, which would tell us that there are black hole solutions. However, if we were to assume that that was the only possibility, then we would be essentially dereliction of duty, our scientific duty. So we have to look for alternatives so that we can see whether the black hole is indeed the right thing. So it's a bit like Sherlock Holmes. Once you eliminate the impossible, whatever remains, however improbable, and there's a lot of wacky stuff about black holes, must be the truth.
So the main idea for most of these alternatives to black holes are to get rid of the pathologies associated with black holes. Most significant one is the singularity at the center. We don't know what to do with. But the other one is basically how black holes evaporate and lose their information. Now, these alternatives don't necessarily do all these things. I mean, certainly you want to get rid of the singularity because that's the one that makes the least sense. But whether these things evaporate the same way that Hawking predicted, that's also not clear. But basically, the main motivation is that these pathologies that exist in standard classical black holes, you want to basically undo them one way or another.
If we want to look for alternatives to Einstein black holes, there's basically two things that we can do. We can tinker with the theory of gravity, and we can also tinker with what the sources are. In other words, what's making up our astrophysical object. So quite a few alternatives to black holes tinker with that source, as I say, the astrophysical object.
These are made up of particles that we know exist, but instead of containing hydrogen or carbon, they contain what are called bosons. We
have these particles that tend to be characterized as either fermions or bosons. Fermions are sort of more or less are building blocks, things like the electron or the proton that makes up the nucleus, whereas bosons are things like the Higgs boson, like the photon, the particle of light. And I guess broadly speaking, you could sort of say that bosons tend to be the force carriers, whereas, the fermions tend to be the stuff that we're made of.
So the idea of a boson star is that if you have a type of a scalar field in the universe, which is very light, so the only scalar field that we know exists in the universe, which is fundamental, is Higgs field, but it's a very, very heavy field. But you could imagine fields that are very light, so much so that their size, the Compton or the Broglie wavelength of these fields is very big, size of what a black hole would be. So these are, we haven't seen any such light particle. The heaviest particles, the lightest particles we've seen are something like electron or maybe even a neutrino, but we need something much, much lighter than electron or neutrino. But if this kind of fields exist in the universe, they could form structures that are compact, that look like a black hole, but not quite as compact as a black hole.
These are huge condensates. Theory makes it possible. And they can almost look like black holes, but they are slightly bigger than black holes.
It can be possible for them to be very compact, very small, but not quite as small as the black hole would be. And they have a sort of quite a sharp cutoff surface so that outside they look pretty much the same as the black hole, but instead of having this bizarre horizon and indeed a singularity, which was what Roger Penrose told us was inside the black hole, instead of that, they're now all regular. And actually, that's another reason physicists kind of like these alternatives, because we're always rather deeply uncomfortable with, I called it a singularity, but it's basically a place where everything goes wrong, where the laws of physics break down.
Gravastar is an interesting and kind of old idea of when I was a student, actually, back in early 2000. And it has to do with the thing which is kind of interesting about the way up the nature of the black holes, that universe with a dark energy, which we seem to be observing, seems to pushing everything out. Everything is moving away from the center and being pushed out. Black holes are sucking everything in. So what if inside of the black hole is like the black hole inside out, which is like our universe, which is filled with dark energy?
This is kind of a weird solution, where what you have is sort of your normal black hole type of, outside the object, but instead of just carrying on with the same sort of Einstein-type Schwarzschild solution, it's called, this black hole, you have a shell of some form of matter, and then inside it, you put, and this is going to sound really bizarre, you put what we would call an expanding universe. Now, as I say, that might sound a bit cracked, but if you think about it, the black hole kind of wants to suck things in. So if you want to fight against that sort of being sucked in, maybe an expanding universe is kind of the obvious thing to do. And so specifically what they put is this particular form of an expanding universe that cosmologists believe happened in the very, very early universe in inflation. So it's a very special source. It's something which we call a cosmological constant.
Some theorists have proposed that the inside of that looks like our universe. It's called Friedman-Robertson-Walker universe. It just looks like that. But the outside, of course, is like a compact object. You can't tell it except by probing the surface itself and trying to understand what is the size of this surface.
So the original idea of Gravastar was basically inside of the black hole, instead of a singularity, an empty space, you actually have type of dark energy that pushes everything out. And you have some sort of a surface, some kind of a surface. So it is like a star because it has density in it and it has a structure. But it is a very weird star. It's a dark energy star, and it has this weird membrane that separates the empty space from this dark energy space. So outside would look like a black hole. Inside is this dark energy universe, looks like a universe filled with dark energy. And then there is this membrane that separates them. And then exactly where this membrane sits would tell us like how different from a real black hole or a general relativity black hole it looks like. So if the membrane is very far out, then it would be probably very different from a black hole. You could see the membrane and its properties. If it's very close to the horizon or inside the horizon, then probably we won't be able to tell the difference. But then also it would be hard to see how a membrane could sit inside the horizon. It would be a very weird membrane.
Okay, so in the traditional idea of a black hole, because of its self-gravity, all the matter shrinks to a singular point in the center with infinite density, and everything else is empty space. And in that, we define a boundary called the horizon, which is the region from which even light cannot escape. Now, string theory is a theory of quantum gravity. So now we take into account quantum effects. And then if you start looking at this problem afresh, you find that once matter gets sufficiently dense, it doesn't actually keep shrinking under its gravity. At some point, all this matter just keeps fluffing up due to quantum gravity effects into a ball, which we call a fuzzball. And the ball is just slightly larger than the horizon would have been, so there is actually no boundary from which light cannot escape. And this is what gets rid of Hawking's information paradox.
There isn't an information problem with white dwarfs, and there isn't an information problem with neutron stars. The problem is the horizon. A black hole has a horizon, and that's what creates the Hawking radiation. The whole point about fuzzballs is there isn't a horizon. It's another state of matter that can hold up a huge amount of mass and stop a black hole horizon forming. There is simply not an information problem with fuzzballs.
The whole key to solving the black hole puzzle was that in string theory, the objects are not point-like particles which can race around the way we always thought in particle physics. They are like strings and brains, which are what we call extended objects. They have a size. So the reason the black hole puzzle was solved is that anytime you try to make a black hole out of point-like particles, they all rush to the middle the way everybody thought. But if you put energy in a string, it can go into two places. You can make the string move faster, just like a particle, but you can also put it into stretching the string. And there are many more ways to stretch a string as compared to just moving it. And so just on the laws, based on the law of thermodynamics, the energy actually goes preferentially towards stretching the string. The guy becomes so big that it becomes this fuzzball, and that's how the puzzle was solved.
They are constructed out of theory in which the object that forms might be something called a black shell. This is a high dimensional object. It is possible in certain exotic higher dimensional theories of gravity. They still have some properties of black holes, but they're not quite that.
But basically a black shell would be some sort of a localized object that sits there. And I guess just the main reason people would call the shell is that it's thin, as opposed to something that's fuzzy, like maybe a fuzzball or a Boson star, which are kind of very big fuzzy things. But yeah, black shell is just very localized. It looks very much like Einstein's black holes, all the way until you hit the shell, and then other things happen as you hit the shell.
There are very number of limited solutions that produce black holes, and they all fall into same category. You have Schwarzschild's black holes, Kerr-Newman, and there is like 3 parameters that identified, and that's it. You could modify, think about if general relativity modified, then what happens to these particular ones in 3 + 1 or 4 dimensions. But then if you have extra dimension, you have this, then you have menu of solutions. They don't have to be like a spheres, for example. And the one example that is nice is this black rings, for example, because now it can be elongated rather than a spherical black object. You could have something that is extended this in an additional dimension, and then you can look into it. Is it stable? Does it stay like that? Or it can at some point break down into mini black holes.
Now, the idea of Planck stars is that at some point when you get close to forming a singularity, then you have some quantum effects that turn things inside out. So your crushing basically singularity becomes a banging, like a Big Bang singularity. And then out of that, you make a white hole. Basically, you form a black hole or something very close to the black hole, wait for a while, and at some point it explodes. And it's called Planck stars because this presumably happens sometimes around when you get close to a Planck density. So there's a transition from black holes to white holes.
This is where you need quantum gravity, because the black hole shrinks to a very tiny size. It shrinks till it reaches a minimal size at the Planckian length. So there you definitely need quantum gravity. And loop quantum gravity provides concrete calculations to know what's going on there. It solves the problem of what happens in the interior, because you don't have a singularity anymore. Quantum gravity cures it, but also it tells you what happens in the exterior. So the final objects really behave as a quantum particle in a superposition of a black and a white hole, just like the Schrödinger cat that is dead and alive. Here, our particle is both black and white, and is just a stable object stabilized by quantum effect that lives very long.
Planck stars are a candidate not only for black hole alternatives, but also for the mysterious dark matter that is believed to pervade the universe, which physicists still haven't identified.
So in loop quantum gravity, we may have ways in which this scenario can turn as something concrete, and not just for big primordial black holes, but also for very, very teeny one, as loop quantum gravity allows for small black holes to turn into remnants. Quantum objects that have just the Planck size, namely the mass of a particle that is just Planckian, but very, very teeny, having the area that corresponds to the Planck area, the minimal possible area in the universe. So these objects are just the perfect dark matter.
With these and other alternatives to black holes, the question remains how to distinguish them from the classical black holes of general relativity.
It's the million-dollar question, isn't it? I mean, it's kind of frustrating because the black hole itself, by that event horizon, that sort of horizon between what we can see and what we can't, sort of almost by definition, you can't get there to touch it or to measure it or to see it, because it is, by its own definition, there's something we cannot see behind. So instead, what we have to do is to look for the implications.
The implications of black hole physics should be revealed by gravitational wave observatories like LIGO and its successors.
When you have two black holes that sort of are in one of these, what we call a binary system, i.e. there are two orbiting objects. For example, in our solar system, we've got the sun and we've got Jupiter. It's quite common to have two large astrophysical objects. Now, if these two just happen to be black holes, then eventually, they're orbiting, they're spinning around each other, they're slowly emitting these gravitational waves, and very gradually they spin towards each other and then they merge. That is a very violent event, and it sends this massive burst of gravitational waves out across the universe. And so that is indeed what the LIGO experiment was built to measure, and did indeed measure. And it's been a game changer really for what we imagine to be our population of stellar or rough stellar mass black holes.
How do we convince ourselves that we're looking at black holes, that we're listening to black holes out there? And you can do this also by understanding very carefully the sound from these objects. And I showed 7 or 8 years ago that if you're very patient, okay, you listen to the characteristic sound from a black hole merger, and if you're patient and you wait, and if there's an echo of this sound, of this music, if there's a late time echo in the signal, that's going to tell you with all likelihood that those are not black holes. We call them echoes of gravitational waves. LIGO is searching for them, and I think it's a beautiful because it's a robust signature of beyond black hole physics. If there's things that sit at the horizon or close to the horizon of black holes, they are going to give us echoes of gravitational waves. If it's not anything that doesn't have an horizon, that's just a deep well, but not a bottomless pit, that will always give us echoes. That was the thing that we understood in the last 8 years. We understood that what LIGO saw, this beautiful, we call it a ring down wave.
The idea of ring down is that if you hit a bell, it's going to ring and it's going to ring down. Black holes are kind of like a bell. You cannot hit them with a I don't know, with a hammer, but they can hit each other and then start ringing.
It's just radiation. It's just the light ring of black holes relaxing to something very quiet. But it's not an evidence that there's a black hole out there. So whenever you have a deep well, but that's not bottomless, you're going to get echoes. So we're actively looking for that. We want to know how to model this. So we want to model alternatives to black holes. It's a very active field of research, and we have the data. It's a beautiful thing. We have the data now, and Lisa is going to give us information that's 10, 100, 1,000 times more clear.
LISA is a space-based gravitational wave detector. And unlike LIGO, which has 4-kilometer arms, LISA's will be a whopping 2.5 million kilometers, giving us huge improvements in resolution and the ability to see mergers of supermassive black holes, something LIGO cannot do. But LISA won't be launched until the next decade. So what does the data say now?
I think early on there have been some interesting hints, and I was involved with the groups that made discoveries of these hints. But unfortunately, they haven't been very strong, and it seemed that most of the black hole events that have been observed, about almost 100 of them, don't show any of these hints. So there are like a handful that show interesting hints, depending on the method that you use. So I think it's fair to say that there is no confirmed detection of echoes in the data. We have limits on the type of echoes that could exist. So they're not very, very loud.
But even if we show 10 years from now that we don't see anything, that we don't see echoes, we are going to be constraining the presence of matter down to the Planck scale away from the horizon. It's impressive. We're doing what we would think only accelerators at CERN would do. We're constraining things at the Planck minuscule scales away from the horizon. It's so exciting.
The good news is that now we have a theoretical understanding of how loud echoes should be. And with the current generation of gravitational wave detectors, we cannot confidently detect them or rule them out. But with the next generation, we should be able to confidently either detect them or rule them out.
Another possibility is to look at images taken by radio telescopes.
Right near the horizon, gravity is so strong, at least for most astrophysical black holes, that it would rip us apart and be physically impossible to, say, send a probe down to explore. So what we end up doing is looking at the predictions, looking at what Einstein gravity tells us, and we ask, well, what happens if the black hole sucks, let's say, some other star or material that then heats up massively so that it starts emitting all sorts of light? How would that light travel to us? What would it look like? And so that's one possibility. And that is behind what the Event Horizon Telescope did to observe the shadow of a black hole. So we can't see the object itself, but we can see the shadow that it puts between us and this, light behind it or emission from things that are being sucked in. That in and of itself is not directly seeing a black hole, but this is why it's so important actually to think about alternatives, because if we can find alternatives to black holes and then say, well, if something was sucked in and it sort of shone some light at us, and that light looked very different from what the Event Horizon Telescope saw, then we would know that's not an option.
50 years ago, nobody thought that there are black holes in the universe, let alone at the center of every galaxy. But now everybody talks as though this is an established fact. When I was doing my PhD, there was absolutely no firm evidence that these are black holes. So it's very fascinating to see that we have come a long way accepting the black hole paradigm for these objects. But what else is there in the universe? That's what science is all about.
This film was shot at the Black Holes Inside and Out conference in Copenhagen, and we have several upcoming films with many more experts who reveal the cutting edge in black hole research. So stay subscribed and find the link to our black hole playlist in the description below.